What is e? The two most common logarithms used are log to the base 10 and log to the base e. Why are they the most commonly used logarithms? How do we really understand them? Log to the base 10 is kind of intuitive. It's easier to talk in multiples of 10. 10, 100, 1000 and so on. Log to the base 10 gives us an easier scale to work with. Log 10 to the base 10 is 1. Log 100 to the base 10 is 2. 1000 to the base 10 is 3. And we can see that the multiples of 10 can be managed with a scale of natural numbers. But log to the base e is what I'm deeply interested in. It's called the natural log. And it's also written as ln. Yes, log to the base e is also written as ln. So log 20 to the base e can be written as ln of 20, the natural log of 20. What is this e? Some call it a magical number. Some call it an irrational constant. Some call it a Euler's number. But the harsh truth is this: very few people actually understand what e is. To get to e, we first need to understand growth. Let's say a particular thing doubles every time period. On this timeline, this is today, and every unit is one time period. Assume you have $1 with you. At the end of the first time period, this dollar doubles and you have $2. At the end of the second period, $2 double to become $4. And at the end of the third period, we have $8. How do we look at this growth? First, we see that the numbers at the end of the time periods are powers of 2. It's in the form 2 to the power x, where x is a non-negative integer. 2 raised to 1, 2 raised to 2, 2 raised to 3, and so on. This was one way in which we looked at double growth. Another way to look at it is that there is 100th% growth every time period. 1 plus 100% of 1 gives us 2. $1 was increased by 100% to get 2. In the second time period, $2 grew to $4. 2 plus 100% of 2 gives us 4, and so on. So doubling the value is the same as a 100% increase. So 2 raised to x can also be written as 1 plus 100% raised to x. It's like you're getting a 100% return on your investment. But hold on, we are making an assumption here. We are assuming that growth happens in a discontinuous fashion. We are seeing growths in steps here. What about the time in between two time periods? We are seeing no growth in between. No growth and it suddenly doubles. Again no growth and suddenly doubles. But hey, that's not how nature functions. Everything or every kind of growth happens gradually. If your height today is 4 feet, you suddenly won't be 5 feet a year later. Your height gradually grows. When we started, we used to get around 30 views a day. And after a year, we started getting around 4,000 views a day. It doesn't mean our view count just jumped one fine day. It gradually increased. So growth in nature is never really discrete or discontinuous. Let's see how it really works. We take the example of $1 growing over 1 year at a 100% growth rate. First, we look at the annual growth. Based on what we saw, at time 0, we would have $1. And at the end of the year, we will have $2. This doesn't seem right because all the interest cannot appear on the last day. To make it slightly better, let's divide the year into 2 equal parts, 6 months and 6 months. Splitting that 100%, the growth would be 50% in the first year and 50% in the second. It would look like this. Our initial dollar earned 50% interest in the first half to give 50 cents more. Now what happens in the second half? $1.50 remains as is. The growth is 50%. So 50% of $1 will be 50 cents. And this time the 50 cents also earned a 50% interest. That will be 25 cents. This 1.5 is the sum of our original dollar and the 50 cents we made here. So at the end of the first year, we have our original dollar, then we have the dollar that made our original dollar made, and we also have the 25 cents that these 50 cents made. a total of $2.25. This is better than doubling. If we want to understand this using a formula, it would be 1 plus 100% over 2, the whole squared. We had half the growth rate over 2 time periods. This is also referred to as semi-annual growth. Let's push ourselves further. What if we had 4 equal time periods in a year? We have divided 1 year into 4 quarters. This is how it would look. Looks messy, but it's actually very simple if you've understood the concept. It's 25% growth every quarter. The formula would change to 1 plus 100% over 4, the whole raised to 4. We would approximately get $2.441 at the end of the first year. I suggest you pause the video and understand the quarterly growth diagram really well. The 100% is nothing but 1. If 2 time periods, then we have 2 here. If 4 time periods, then 4 here. So the formula for n time periods would be 1 plus 1 over n, the whole raised to n. Clearly, more the number of time periods, higher will be the returns. This will give us the dollar value at the end. I probably know what your greedy brain is thinking. Is it possible to get unlimited money? Let's make a table now. Number of time periods and the dollar value in the end. If it's just 1 time period, the dollar value is 2. If 2 time periods, then $2.25. If 4 time periods, then $2.44. If I divide the year into 12 equal time periods, my return will be higher than this. If I divide it into 365 equal time periods, it will be even higher. This tells us that $1 at the start of the year will become these many dollars at the end of 1 year if the number of time periods is 365. So if we increase this number significantly, that is if we increase the number of time periods significantly, will this number also increase significantly? Okay, here are a few more calculations. The number of time periods here is 1 million. Notice that the returns improve, yes, but they converge around a value which approximately equals 2.718. And that is your beloved E. We can't get infinite money after all. What would be a layman-friendly explanation for E then? It is the maximum possible result after continuously compounding a 100% growth over 1 time period. Yes, that's E. Don't forget, we had assumed a 100% growth here. And that's what E is. It's the maximum we get after a 100% continuous compounding growth over 1 time period. Notice what compounding does. The first result is 100% without compounding. $1 would become $2. But after continuous compounding, $1 will become $2.718 approximately. That would be a growth rate of 171.8%. That's like the maximum growth we can have. So E is approximately 2.718. It's an irrational number, which means the digits after the decimal point do not repeat and go on forever. Just one last question. What if the growth rate and the time period change? Will E still help us? Absolutely, there's no problem at all. In general, the growth after continuous compounding is given to us as e to the power r times t, where r is the rate and t is the number of time periods. So if we have a 200% growth for 5 years, then it would be defined as e to the power 2 times 5. We squared e to include 200% growth and we raised it to 5 as there are 5 time periods. It'll give us e to the power 10. E is nothing but the maximum possible result after continuously compounding a 100% growth over 1 time period.